I'm going to do a little bit of pre-production here, if I can. Maybe not. No, I think we're. Oh no, I can do this. Okay, so pretend that you're not here. So I'm coming, say, 10 minutes early, and then there's something I want to hide here.
Should I distract them?
No, it's all right.
Everyone close your eyes.
Yeah, I mean, it's okay if you see it. It just. It's just more exciting if you don't. If you do see it, then it's foreshadowing. So you can say, whoa, what the devil? This guy. All right, so the stage is set. I'd also probably write this up. All right. So I want to talk today about something that I think is absolutely wonderful. It's Japanese temple geometry, and so it's got a little bit of history, a little bit of geometry, and a lot of very lovely pictures. Okay, so interrupt me as we go if you have any questions. So from about 1630 to about 1850, Japan was isolated from the rest of the world. There's no travel in or out of the country. And this was punishable by death. So it's very strictly isolated. But in that sort of situation of peace and prosperity, the culture flourished. And so we see flourishing not only in, say, literature, painting, but also mathematics. Let's say particularly mathematics. Say including. But unlike other situations where mathematics blossomed in the world, so I'm thinking, say, the ancient Greeks, or even the European Renaissance, this activity wasn't restricted to small groups of people, specialized mathematicians, specialized segments of the population. This was really a democratic outpouring. So you saw contributions from men, women, children, the very rich, the very poor, carpenters, farmers, professional mathematicians. And we have again, in contrast to some of the other periods of mathematical bursts in human history, we have a detailed record of what you might think of as folk mathematics. And these are in the form of what are called Senkaku, or mathematical tablets. And that's what I want to talk about today. So it's in the form of Senkaku.
Is this going to be on the exam?
It definitely is the exam. And so this is probably unique to the world. The idea was that people would work on problems I'm going to talk about some geometry problems, but I mean, it cut through all different branches. So you saw things like problems in combinatorics, problems in what we would now call integration, differentiation. And they would work on these problems just for the fun of it. And when they found something that was particularly beautiful, they would feel this, well, ostensibly a profound sense of gratitude, and they would paint it onto a tablet. And so you would see these very beautiful statements of the problem, the result, and no proof. And then these would be hung in the temples and the shrines all over the country. But then you can also see that there's another worldly dimension here, which is to say, look what I've done. Can you do this? This is amazing. Right? And so these mathematical tablets, some of them are still existent. We also have travel diaries of mathematicians of the time who went through and documented on their travels different results all over the country. As I said, this is widespread, and everyone's contributing to this. It's really a unique situation. And so as I say, what I'm going to talk about today is geometry. So I'll give you a sense of the types of problems, a very simple problem. We get our feet wet, and then there's some fancier problems under this board. I'll get there in a second. Okay, so let's look at an example problem. Or let's not call it a problem. It's really a result. And so take some drawing. But what I have here are three circles, R1, R2, R3, and so I'm going to label them according to their radii. So circle R1 has a radius R1, circle R2, and so on. And these guys are tangent to one another. And a straight line. And so the question is, how are the radii related to one another? So this is not how it would be. This is not how it would appear on Senkaku. I mean, in a Senkaku, we would just have this picture and the result that we'll get to in two boards. But I mean, there's no drama in that. So I'm going to make it a little bit more theatrical. And I'm going to deliberately go through this a little bit slowly so that if you want to try your hand at it, I'm just scribble in the margins as I go. Okay. All right. Is everybody clear on the problem setup? Okay. So I'm going to look at one way of solving this. Okay. I mean, I'm sure there are many. But for what I'm about to show you, I'm going to use the Pythagorean theorem almost exclusively. That will be my only tool. So I'm going to put up a couple preliminaries. The first one may or may not be self-evident. So I'm going to put it up as though it's self-evident. If you don't think it is, then just take some time to prove it to yourself. And that is that if you connect two tangent circles, connect the centers of two tangent circles, the line connecting these two centers will pass through the point of tangency. Okay, so connect the center of two tangent circles passes through the point of tangency. Tangency. All right. And then the second, and hopefully it's not obscured by the croissants, is the Pythagorean theorem. Which is to remind you, it says that a right-angled triangle is characterized by this theorem, which says that the sum of the square of the sides is equal to the square of the hypotenuse. All right. And so the method of approach that I'm going to take today is a tried and true mathematical method. I'm going to try to find two different ways of saying the same thing. And if you want really sort of a matchbox definition of mathematics, that's probably serviceable. Right? We're always looking for different ways of saying the same thing. Bless you. And that's what an equality sign means. All right. So what I'm going to look at is the distance between these two radii as projected onto the line. I'm going to find two different ways of expressing that length, and that's going to give me enough constraints to figure out how these radii are related to one another. And again, I'm going deliberately slowly, so if you want to jump ahead, you can. Right? Because you can see that these have to be constrained in a very strong way. If one of these circles gets big, all of the other circles need to get big in order to maintain that tangency. All right. And so the first way, so what I'm going to look at is so this is distance not as a crow flies, but the distance as projected down onto this line between the radii of the biggest circles. And so or sorry, the centers of the two largest circles. Okay, and I'll call that distance x, and I'll show you what I mean in a second. So I have R1, and I have R2, and I have the little circle here. Okay, and so the two ways that I'm going to approach this is I'm going to either calculate it directly by just taking into consideration the two largest circles, and then on this board, I'll look at passing through the center of the smallest circle. I mean, the way that I move my hand on the board suggests that what I'm going to be doing is drawing right-angled triangles. Okay, so the first trip is just using R1 and R2. And so what I'm going to do is draw a right-angled triangle that connects the centers of these two circles. And now the really, so that's sort of the epiphanic moment, right? If you can see that that's something you need to do, the rest sort of falls into place. But that's not an easy thing to notice. Okay, but having done that, now what's the hypotenuse here? R1 plus R2. Right? We can use this preliminary result here. And we know that, here I'm going to blow it up a little bit. This is the point of tangency. This guy's R1 plus R2. This leg down here is what we're looking for. We don't know what that is. How about the vertical leg? Beautiful, right? So it doesn't matter which one you call the bigger of the two, right? If you had drawn it in your margin the other way, just flip your page over and hold it up to the light. It really doesn't matter, right? And so you take the bigger, you subtract away the smaller, and that gives you this distance along the vertical. And so in my drawing, that's R2 minus R1. And now I can use Pythagorean's theorem to get an expression for this x in terms of R1 and R2. Okay, and so a little bit of algebra is going to follow, not a lot. So again, what I have is, from Pythagorean's theorem, is that the square of this hypotenuse is equal to the sum of the squares of these. And it looks like it's going to be maybe messy, but you blow it up, and a lot of things cancel out. And so I'll go through this one in some detail. I mean, like when I say some detail, I just mean one extra line. But later, we'll be doing this again in a second. Okay, so now it looks even worse. But you notice that there are common terms. So the R1s and R2s cancel. And I can bring all the R's over to one side. And so I get, in the end, that R squared is equal to 4R1 R2. So hopefully that's clear. Is that? Oh, or let me go one more step, and then it should be crystal clear. So 2 square root R1 R2. Okay. Any questions on that? So that's just Pythagorean's theorem. And again, in retrospect, sure, it's Pythagorean's theorem, but it's that epiphanic step of actually putting a right-angled triangle right there that's really important. All right, so let's look at the second then. So the second trip is going to take us through the smaller circle. And so we're going to write this distance as a sum of two distances So let me call that XA, let me call that XB. And then my total distance is going to be the sum. And then carrying on as I did over here, hopefully it won't be too difficult to see that you'll get that xa is going to be equal to 2, let me write that like that, 2, all right. So if this guy is R1, this guy is R2, and this little fellow down here is R3, what's this one? Right? So you don't even need to do the algebra. I mean, and I'll fill in the other one. You don't even need to fill in the algebra. I mean, you just, just relabel your circles, basically. All right, so now I'm one step away from sort of pulling the rabbit out of the hat. What I have here then is that x is equal to xa plus xb. And again, I'm being deliberately pedantic here so that you can jump ahead if you feel like it. We get 2 R1, R3, 2 R2, R3. All right, and of course, these need to be equal to one another because it's the same distance. And so in the end, what we have is setting them equal to one another. 2 square root R1, R2 is equal to 2 square root R1, R3, plus 2 square root R2, R3, which is undoubtedly true, but a little bit ugly. And so one more step, and this turns into something absolutely beautiful. And so what I'm going to do now is divide both sides by 2 R1, R2, R3. And what you get is, well, let me write it out. You'll get 1 over square root of R3 equals 1 over square root of R1 plus 1 over square root of R2. Right? Really unexpectedly. But this is beautiful. I won't write it. I mean, it's lovely. And you can see that why someone would want to carve that into a piece of wood and hang it in a shrine. Right? And I think it's worthwhile asking ourselves, is there something that I've done that I'm so proud of, that I'm so grateful for, that I would think to hang it in a shrine or a temple? I mean, think of the sacred responsibility. It's really moving. And you can also see that, how these kind of problems can spread through the culture like a virus. You look at this, and so there'd be a picture like this, there would be a line like this, and the first thing you would say, when you're just walking along, you look up, you say, maybe you say, I don't believe that. Or if you do, you say, how the devil do you get that? And then you say, well, what can I do with this? Why don't I start putting circles down here? You can look at the sequence as it goes down. Well, maybe they don't need to be tangent to a line. Maybe they need to be tangent to some other figure. Right? And you just start extemporizing, improvising. And I mean, that's exactly what happened in this 220-year period. Bless you. And so this is a very simple example, but already hopefully you can sort of see how you might do variations on the theme. But these problems could get very complex. And so I have a couple other examples here, and I won't go through the details. This one is hopefully, I mean, the drawing's not perfect, but hopefully it's evident. This guy and this guy have the same radius. These guys have the same radius, and then this little guy is holding the whole thing together. And so you have circles that are tangent to one another and tangent to a rectangle. And then the question is, how are the sides of the rectangle related to one another? And again, there are thousands of ways to prove it. Oh no, I'm not going to prove it. I'll let the cat out of the bag, though. Yeah, I will. Okay. So if this side is A length, then this guy is square root of 5 times A. Really? And prove it to yourself. I mean, again, you won't need anything more sophisticated than what we've already used. Or this one where we have a bunch of circles tangent to one another inside of a circle, and then these smaller circles inside. I mean, it's very beautiful. Just aesthetically, it's very beautiful. And the result is absolutely baffling. So try to prove to yourself that this is true. That the outer radius of the circle is related to these tiny inlaid tangent circles in the following way. Right, now this is a pickle. And so maybe the last thing that I'll say, I will say this. One hint that I can give you is that trying to do this guy directly is Very difficult. But what you can do is find an inversion mapping, a conformal mapping, that will take this circle and map them onto parallel lines. And then the whole thing falls to pieces. All right? But I leave that to you. All right. Thanks.